small crack results in this huge problem. And to fill that up, it's not a question simply of plugging it in. You've got to dig it all out, get material, put it in. It's a massive engineering job. So this project's really focused upon what we call minimally invasive or small-scale repair. So let's try and find problems really early on, fix them quickly, simply, and then this kind of problem doesn't actually happen, which is what we're trying to do. So in the projects generally we have all kind of autonomous robots. We have robots that can fly, consume things, do things. Sensing is of course very important, sensing on the ground and in the air. We have to be able to apply materials to repair. So we're doing lots of work with how you can 3D print and deposit materials. So it's great to go and find a problem. Not an awful lot of use though. You find a problem and you can't repair it. That's not great. You want to find it, repair it straight away, and then you're done. So looking at how you can deposit material, how you can measure things in a crucial way. But I think also one of the things that probably is least talked about in this kind of sector is technology is great, but it's a balance between technology, people, and also the environment. So we're talking about putting autonomous robots in this context across the whole city. So maybe we'll have, I don't know, 2,000 drones flying around the city. The effect of the project will remove trucks, men digging holes in the ground, women digging holes in the ground. That's good. So there's no digging, there's no trucks. So it clearly has positive impact. What we don't know is how will it affect wildlife? Will the birds get really frightened at all these drones flying around? So we can't just think about the technology, think about the wider social context of this as well. So light, noise, vibration, all of these kind of things can be an issue in that context. We're also looking at how you can define future infrastructure. So right now, we're looking at robots that can try and repair current infrastructure. That's difficult because certainly in the UK, lots of very old systems not designed for robots. We must make sure that when systems get put in, there are actually new systems are being put in that are robot friendly. So get some standards out there, get some robot friendly parts put in that we can inspect and repair more in the future. And I guess the last thing on here, of course, very important, is actually the balance between humans. So lots of concern, I guess in the UK generally, about robots taking jobs and things, in particular in areas like construction and maintenance. So we're working very much to try and understand how we can make sure that it's a positive impact to the community generally, rather than being a negative impact to stuff. So I've talked a lot about sort of general things. I want to give you a flavour of a couple of my projects before we finish. We've got a few minutes yet. So one thing we were doing is we were trying to look at surveying melt lakes in Nepal. So the question here is a melt lake being a frozen lake that at periods of time will freeze, become not a lake, and other periods of time will defrost again. So we want to be able to measure the amount of water in this region at any period of time. And that's difficult, of course, because how do you measure the amount of water there? So one thing you can do, you can take satellite images. That gives you the area from the sky. So you know the area of the water, which is important. But what you don't know is how that area corresponds to the volume. You can guess, but you don't know. So what you want to be able to do is you want to be able to directly measure that. So volume versus area is what we're trying to do. So it's in the area of the Khumbu area of Nepal, as such on here, on the border of Tibet. So it's actually one of our student projects. So one of our level 4, which is like the final year undergraduate students, we're working on this. The challenge is that the lakes that are big lakes near the bottom are fine. You drive a truck there, you get a boat out, you row around the lake, you drop a few sensors in, you can measure it. So the big lakes aren't really a problem. The problem is where there are smaller lakes that are hard to get to. You can't drive there, you can't carry a big boat, it was just not feasible. So what we wanted was a really small backpack portable system we can take to the lake, deploy, and get these maps of things going on there. So you'll see here, this robot here, it has 3 sections. The 3 sections just unplug, go into a backpack, a normal size backpack's fine. You can get there, plug it in, and go. It has these huge clips on here, look a bit cumbersome, a bit kind of ugly, if you like. But bear in mind, it's cold. You're deploying this in the cold environment. The last thing you want is a screwdriver, a spanner, anything like that. So in this case here, you can just pull the pins out, pull it apart in your backpack, and you can go, which is really good. So it carries, on the bottom here, it carries a sonar sensor to measure. So the sonar sensors work by picking out sound. You measure the sound coming back, and you can work out how deep it is. So this middle section here has a sonar sensor in to measure the depth. We also have, on the top here, we have a a winch mechanism. So we're also interested in actually in the thermal profile. So we want to measure how hot it is as we go down to different depths. So in this case here, you'd go there, try and station hold, and you drop the line down and measure the actual temperature at depths going down. So you can see here, an absolutely amazing place. I haven't been myself, but the team that went out there was absolutely amazing. So you can see here the little boat down the bottom here. Maybe you can, maybe you can't see. Beautiful scenery here. Go a bit closer. So it's kind of lost there, though. It's quite a difficult environment. Even this lake, this is one of our test lakes. It's quite I guess, an easy lake to go onto, but it's quite a difficult lake to do things. So very easy to kind of have problems and crash and that sort of thing. This is a video of what it's like to be on a glacial melt lake. So we're driving around now, and what you'll see, of course, it's quite flat. But you'll notice that there are things falling off here, falling off the ice cliff. So not only is it difficult to get there, also quite dangerous to be going around on a boat there. You could get hit by one of these ice things. So it's a good task for a robot to go around there and drive around and see what's going on. You'll see it turn back and look at the guys over here. So this gives you some scale there, the people there. So this is quite a big lake. It's one of their test lakes. They were testing it on. So we used, I guess, for quite a low order autonomy on this. So it's very, very hard for the robot to know where it should go. So it can't really, using vision, detect where the lake is, where the lake edge is. It's very difficult to do that. So what we did, we have a system where we take the boat out, you manually drive the outside. So you see the outside here. So someone's manually driven around the outside. Then the robot itself does what they call a spiral search. So it tries to do, it's not spiral search getting outwards. You can see it's a bit crazy. It's a bit all over the place. It's getting a bit blown around and things, but it's mostly managed to do a spiral search, which is good. And then you look at the volume map here, so you can correlate the actual depth of it to the volume map here, and that's quite useful, so that gives you the idea of the thing. So with this simple boat, we can identify the volume, which is good. Of course, one lake's interesting. We want a general rule. We want to be able to know how these lakes correspond generally, so we can look at photographs from the sky. So if you look at the graph of, on this side it's volume, this side is area. So bear in mind we're trying to get a correlation between volume and area for these things. These blue lines are the larger lakes, of course, the larger volume, larger area. So someone's been on the lake with a boat, rowed around, got some good data. So they started the line off. Our red dots are from our boat, little radio controlled boat thing. The really good thing here is the correlation is fantastic. So from this relatively simple project, we've ended up getting some great papers and some great work. And in fact, now we know this. So now we can pretty much guarantee that for a set of aerial photographs of the area, we can work out the volume, different times of the year. I'm not an expert in the area, but apparently it helps to do with global warming analysis, that kind of thing they're trying to do. I guess it's something to do with the energy stored in the lake, it's something to do with how much is melted, that kind of thing. And the actual work's carrying on, so this was an interesting project, but now it's going on. It's actually a NASA-funded project now. They've taken it across to this project here, which is Understanding Changes in High Mountain Asia, and they're using it to map these kind of lakes. These are quite big lakes, actually. We're trying to map them. One thing we do find, though, in this boat, it's a fantastic thing. It's not great at quite rough water. So it's fine in a glacial melt lake. They're pretty much crystal flat, if that's the right word. Very, very flat anyway. So that's okay. These larger lakes tend to suffer from more sort of turbulence. We're also looking at doing a similar kind of thing actually in the Amazon. So it's interested in mapping the Amazon, its volume, or its cross-sectional volume in particular. So they have models of how water flows through the Amazon. These models, of course, assume a certain size of water flowing. If you don't know the depth of the water, you can't work that out, and that affects things. So what they want to have is a boat that can cope with this river. Of course, it's much, much more turbulent. So we have a project right now looking on a really high-performance version. So the other version was great. It could run for probably a day, 2 days by itself. The high-performance version will be able to cope with quite rough terrain, turbulence, and that would be good for things like the Amazon rainforest, that kind of thing, or Amazon River in the rainforest. So another project here. This project's all about doing actually long-term inspection in the oceans. So you have a thing called ocean gliders. You probably haven't heard of this, but what they want to be able to do is go in the ocean, be there for years. Really, really long endurance, floating around, measuring things like the currents, that kind of thing. But it's very, very challenging to do that. Most of the time, of course, you're actually underwater. If you're underwater, you get no GPS signal. Very, very challenging. So I'm going to play this video here. It takes a little while to come through, but basically this is a glider here. it's been deposited in the water here. So it's working with a guy in Leeds, Jongwei Kim, and this Korean institute here. So in a few moments, you'll see it start coming over here. So it's a good example because it shows how gentle and slow it is. We're not talking at all about really high-powered things. It's gliding around. It's using the waves, using the natural currents to glide around. You haven't got a big motor on it. You can see here there's like no disturbance. It's really slow, really, really sort of gentle stuff. So in a moment, you'll see it kind of appear down here. And that's the idea. So it doesn't need much energy. It can recharge in sunlight occasionally, but you want it just to go away and just float around and measure things with some kind of generation of steering. So you can see it just starting to come down here now. So really slow sort of motion of this sort of going down here. So the challenge here is you're going to submerge underwater and you need to be able to know where it's going to be. So you submerge, you want to go in a certain direction, you have currents, it's really difficult. So I'm not going to give you lots of equations here to worry about, just for the example here. But basically, on board the vehicle, you have what's called an IMU, an inertial measurement unit. As it's getting bumped around, as it starts to accelerate, it can measure its acceleration. It knows what's happening to it. And from the acceleration, you can kind of predict where you're going to go. So if we look at some of these things here, you can do things like working out velocity. So you can try and integrate the acceleration, try and get the velocity. It's very, very difficult. What we can do some clever things. I won't mention it here, but there are some clever mathematical things you can do about collecting data, to do statistical things, to try and improve the estimate to get better velocity. But what you can see here is an example here. So this is a landmass here. This is current. The currents are all over the place, changing in different directions. So what the actual vehicle thinks it is, it thinks it's going to be here. I think it's going to be here. It's actually here. So it goes underwater, submersive. It comes up. As it comes up, it gets GPS. But the estimate of where they think it is a long way off. This is a big problem because you can't just then power yourself off. How do you get back to where you want to be? So using mathematical techniques, statistical techniques, you can try to improve the estimate on this. And you can see here that we have a much better estimate now. So this is the initial position. It went underground, underwater, I should say. And these two things, so the red one is where it actually was, and the orange one is where it is. So we get a much better estimate of where it should be underwater with all this kind of gradients here. So it's quite successful, but it's a very mathematical thing to do. But you have no choice because you're underwater. What else can you measure? You can't measure features. You can't measure GPS. The only thing you know really is actually your inertial movement being pushed around in the water. So that's sort of, I guess these are ocean ones I've shown you all so far. I want to mention the in-pipe thing. People often say to me, actually, what is going to be the biggest robot impact in the next 10 years? And they expect me to say it's going to be autonomous cars, or it's going to be a humanoid robot, or some kind of companion. But to me, the best business case, if you like, the most important thing we can do with robots is inspect pipes. It sounds really dull. The reasons why it's good, though, are because it's a simpler problem. In pipes, there are no people, relatively predictable, albeit environmentally challenging in terms of the actual environment on the robot itself. But the benefits are huge. So if you can repair cracks, there are no digging of the roads, there are no roadworks, there are no associated pollution from the environment. So the business case, I said before, for having robots in pipe is absolutely enormous. So that's really, I think, one of the things we focus on. Autonomous cars have lots of benefits. But to me, it's all about robots and pipes. So I'm going to give you an example briefly of a kind of a pipe robot sort of thing. So we did some work in the pyramids of Egypt in Giza. It's not relevant to water, but you'll see why I'm talking about it in a second. But anyway, in here we have pipes, tubes. So these are square tunnels in the pyramid, and we're building robots to inspect these tunnels. So you can see here, we'll be deploying the robot. It's a square tunnel. I guess it's like a ducting, in fact. So we need a robot that can drive through these tunnels and be able to map them and be able to measure what's going on. So you can see as we climb up here, we can see different features of the tunnel. So you can do all kinds of mapping, very much similar to you would do in a water pipe. You'd drive along, you'd use cameras, you'd use sonar sensors to measure the wall thickness. Right here, we care about really the features on the wall. In the pipe context, you'd often use things like sonar sensors or ultrasonic sensors to see the depth of the wall. So often you care about the thickness of the pipe rather than just the features. In this case, we just care about the features of the actual pipe. And you can see it here climbing here. So it's very similar, like I say, to a water pipe might be. We're driving along here. We have our articulated body. So what happens is the robot gets longer. It has these pads that come out and grip the sides. You'll see in a second the back also has pads that grip as well. So these pads go in, so you can kind of gradually crawl along the path. So this is one way of climbing in pipes. It's called a wall press because you're pushing on the outside of the wall, therefore you're getting enough traction. With this, we could climb up, we could climb along. It's enough force to do all kinds of weird climbing maneuvers in different pipes here. So that's a simple one. The problem with that, of course, it's quite a long, straight robot. We've also built more complicated robots to go around bends and that sort of thing. So in this case here, we've got quite a complex robot. It has 12 different actuators. These pads here are what grip to the pipe walls. And you'll see here it moving here. The reason it's so complex is because you want to be able to choose, if you approach a T-junction in the pipe, you want to be able to choose which way to go, you want to be able to rotate it around. So you can see here what it's doing. It's climbing, but as it climbs, it's also spinning. So you have control of rotation, as well as control of direction, and some control to some degree of which direction you go in. So you can choose which direction. For those of you who know about sort of robotics and things, effectively it's a Stewart platform. It's like a Stewart platform which has two plates that has lots of actuators on here that can control the two plates, and the plates can also extend and grip the pipes. So it's an example of a water pipe robot. Of course, one of the challenges we have is we don't want to block the water pipe. So ideally, it would be quite slender. So this was actually designed to be hollow. Right now, it's full of all kind of weird electronics, it's a prototype. But effectively, in a skeletal form, if I go back, in a skeletal form, it's quite thin. So you have an outer casing, water can flow through the middle, so potentially it's going to be relatively low drag. What you don't want to do is put in a big object if you can help it. So if the pipes were metal, some pipes are, most pipes aren't actually for water. If they were metal, it's much easier. You put in small climbing robots. So we have here, this is actually designed for gas pipes, but small robots that can climb in metal things. You can grip on the surface, and you can drive around, and you can spec things. So in the gas industry, working a lot on these, particularly very large bore gas pipes, to inspect them with magnets. I'll just show that again. It looks quite simple. So the transition between flat and upright on here looks easy. It's actually really hard. If you're not careful, what happens is either you stick to one surface or the other surface. The ability to be able to drive is actually really difficult. Of course, the worst case scenario being a square, but there are sort of junctions and that sort of thing that might be difficult. What we want to do in the gas domain is there are entrance pipes coming in, quite small diameter pipes. We want to be able to drive through small pipes into a very large pipe, survey the large pipe, and then drive back out again. But that means going from, basically you've got a perfectly round pipe, a pipe comes into it, you need to be able to drive from the outside of this and drive into the pipe. Really, really hard. So we're not quite there yet. We can do some things, we can't quite do that. So I'm going to talk a bit more about sticking to things. I mentioned magnets already so far. Of course, you're saying, okay, well, water, how can we stick to things that are wet, that kind of thing. So it's actually a medical application, but it's very relevant to wet surfaces. So we're doing some work building small robots to do surgery. So the problem is that you have, you're doing laparoscopic surgery for the human. So you have this thing where you're doing surgery through a small hole. You want to minimize the number of holes, but you want to see what's going on. So you're doing surgery through a small hole, you want to be able to do things. How can you minimize the actual effect of that? So, of course, when you perform the surgery, you inflate the stomach. So bear in mind, you've got a small hole, you put gas in there, your stomach becomes very big. So there is space in there. So how do we put a mobile camera inside the body? That's the question. Of course, you could walk along here, so you could put a small robot inside and try and walk around here. But you can imagine trying to walk around all the tissues, all your organs, intestines, really, really tough. So the other approach is, let's try and walk on this surface here, the surface of the stomach. So it's inflated, there's plenty of space. The surface is very sticky, gooey, difficult to actually walk on. You can imagine kind of slimy, but it's clear and it's flat, which is a good thing. So the question is, how do you stick to wet tissue? So we look for inspiration on this. So you don't want to have metal things. If you start sticking metal feet into it, gripping it, you're going to damage all the surface. You want a very gentle thing that can stick to very wet material. So like this, some kind of robot in here that can do this. So we took inspiration from the tree frog. The tree frog, of course, lives in the jungle in the Amazon, and it has feet that can stick to wet leaves. Very slippy, very wet leaves. So that's what we tried to do. So wouldn't it be great to have a frog that you could put in your body for surgery? Not a real frog, of course, that would be pretty harsh. But in terms of a robot version of this that could walk around inside your body, that would be a really good thing to do. So the question is then for the research, how do frogs stick to wet tissue, wet material? How do they do it? If you look at their feet, they have what they call micropillars. So their feet have these very small patches on them, and they have these gaps. And when you touch wet material, these effectively you get water on both sides, and they form what's called a fluid bridge, and that causes some kind of adhesion. So effectively they're quite sticky in that. So we went away and we tried to fabricate these. So I showed you very early in the beginning about manufacturing at different scales. We talked about manufacturing at the big scales, small scales. In this thing here, we're using very, very small laser-etched, light manufacturing sort of things to make incredibly small pillars that are like the frog feet. So the naked eye, you can't see this. For the naked eye, it's totally invisible. You can't feel it with your finger. They're gone. We made them. So if you look at an electron microscope, you zoom in, you see really, really small micropillars, and that's what causes the adhesion force. It's quite a low force. We're talking about 20 grams per centimeter, but perfectly adequate for a walking robot to walk around in skin tissue. So we've gone from that, then we thought, okay, let's try and build a robot to do this. So we went away trying to build a robot to do this. And here's the robot here, example of the robot. So it's quite a complex robot. So it has 8 different motors. So again, we talked at the beginning about motors. This has micro motors, or very small motors. They're 5 millimeters squared, so they're really small motors. So a motor in here, in here, in here, in here, and also motors in here that push these out. So you have all these motors inside there that push them out. So at this scale, of course, too big to go inside a human body, but just an example. The motor's probably the right scale, but the thing is bigger. And you'll see here an example of it walking on metal. So we've just changed the wet tissue stuff for metal, for example. And you can see here it's walking okay. It can walk around on the surface. You see the motor here, very, very small motors, very, very small, 5 millimeter motors, so really titchy little things, but provide enough force to be able to move, to do things, move around. One of the things with this that's very hard to manufacture, which we'll come to in a second, when you stick to material, if you push it on, it takes not much force, but to pull it off is very hard. Of course, by definition, what you're trying to do is you're trying to make the maximum possible adhesion force you can, sticking force you can. What the tree frog does, it puts its foot on. As it pulls its foot off, it bends its feet, it curves its feet. So if you peel off your foot, the force required to remove it is much less. So in here, you can't see in the big video, I'll show you in a smaller video, we deliberately made that as the pad comes off, it slightly twists it. That twisting motion reduces the force, makes it easier to pull off. So you'll see here the back end here comes off first. So it's just applying a little bit of a twist, and that reduces the force quite a lot to pull it off. Otherwise, you're wasting a lot of energy to try and pull your foot off from you doing it. So it can be done in that context. I should say on here, though, that we are obviously still a long way off, actually, the challenge of making them to be the right size. So right now we're 60 millimeters. To try and fabricate them smaller is a massive challenge. So the actuators are okay. This was made by one of my PhD students, in fact, and he spent weeks with tweezers, small metal bars, trying to assemble it, trying to get it to work. So it's just not good enough. So in Leeds we have a whole facility for fabrication of quite complex systems. And in fact, using this was an example to get the funding. We said, look, we can do this amazing stuff. We just can't build great robots. So we have this facility now saying we can manufacture these things at different scales to very high precision. That's what we can do. And one of the things we're trying to do is what we call minimal assembly. So 3D printing that can print things that work in one go. So you press print, it would make this in a functioning form, and there is no assembly, which is, of course, what we want to try and avoid. So going forwards, really our vision is much more around, I guess, inspection of pipes, but with the smallest possible robots. So I've shown you robots that are quite big. I've shown you robots that are quite small. In this case, we want to have swarms of small robots. So you can see here the illustration of what we've got. So little fish, if you like. That's what we want, little fish that can swim around in the pipes and do things. So using all the things we've seen before, maybe it's using some of these smart actuator technology, certainly using micro manufacturing techniques. As the water flows, of course, it needs to be able to go and stick to surfaces so it doesn't get washed away. It needs to be able to swim ideally against water. If you're going to swim against water, that's really, really hard. So we're struggling with that, this kind of thing. It's fine when you've got like a full bore press, like the Egypt robot, for example, I showed you. A full bore press, you can get really quite large forces. If you're trying to stick to the wall, hold the wall, you can perhaps use some suction for a small period of time, but not very long. So there's lots of challenges around how you do this, but we're looking for, across the UK, we've got a consortium trying to do this right now. So building these micro robots that can swim around and doing things. As part of this work, we're also looking at how you actually go about mapping them. So we mentioned about mapping pipes. What you want to be able to do is able to have systems that can understand like big data things, what's being mapped, what's not being mapped, and try and bring it together. So we have all these systems on that. But as I mentioned before, data communication, this is really hard. So you have 100 robots in the pipe network. Communicating from them to the outside world is really, really hard. So we can do things like communicating robot to a communication node. We can do things like, let's spray the material. So maybe it finds a problem, it sprays the location with some kind of marker, then another robot comes down later on to fix it, that kind of thing. But the communication is a problem, the energy harvesting is a problem, this manufacturing is a problem. So it really is a grand challenge, and hopefully we're trying to solve that, but it's probably going to be a good 10 years off, I guess, in that context. Okay, so I've gone through robots for water. I guess the thing to point out here, just to summarize what we talked about, they're really good, I keep saying using business case, but I think these days we have to say business case. Business case meaning economical, societal impacts to do this, which is good. The challenges are very hard. Water is a difficult environment, high pressure, low temperature, corrosive environments, very challenging. But you can see with some good design, we can produce some good things. And I'm sure that some of you will go away at some point and start companies to make these robots that can work in water. And I think if I was starting out now, I'd be going away and I'd be making robots that can go in water pipes and making a fortune. Okay, thank you. Thanks.
Any questions?
You might have addressed this because I missed the first part of your talk. But towards the end, you were talking about the swarm drone, the swarm network.
Yeah.
What have been your experiences with the networking question in terms of coordinating these in the presence of dynamics? And what prospect do you see for that?
So I think that the swarm thing is very difficult. So we're taking the approach really of biology inspired. So we have, it's not my area of research particularly, but we have a team member looking at ants and how ants can do things and how they can do communication. So it's communicating, but also the least possible amount of data, low bandwidth. So ants don't communicate hardly at all, but they can communicate things. Potentially, say, marking the area for certain things. So I guess in terms of answering your question, we haven't done a lot of work, but we intend to use this inspiration from ants to try and minimize data flowing, communication, and make it as simple as possible, because it's one of the biggest barriers, that's for sure.
So just as a follow-up to that, so there's this animal-inspired idea of minimal communication so that some global dynamics emerge. Yeah. But then there's this other idea of can you have not enormous but significant communication where you can acquire the state of the network of the drones and take decisions like who should go after what. And in the US, the DoD experience has been that those networks don't scale very well. Okay. Conversely, there is a need to grow the size of those networks. So have you considered that question where it's more than just single bit communications between swarm nodes?
I guess the answer is no. So I think, like you say, I think we are very worried about trying to do large bandwidth things, and I think probably it can't be done very easily anyway, that's for sure. So we're trying to avoid that as much as possible. I agree that if you could do that, that'd be amazing. But I think we see them as being much more animal-inspired. They're kind of self-autonomous, self-contained things, passing small amounts of information. Of course, the negative thing of that is you don't have central control directly. It's very hard to kind of say, everyone come back, because you can't communicate with that well. But I think for the reasons you say, I find it very hard to imagine how you'd have a large network that you could talk to and you could scale. I think it's too difficult.
Maybe we can chat off that.
two questions. You said you have a PhD student who is working on these robots.
Sorry. Yeah.
Okay, so whenever you do a research which involves these robotics, when you write a technical paper, what are the things which you cover in the technical paper is one question. And another question for the student community here, if they want to build a quick robot, what are the do-it-yourself kind of kits which are available on Amazon or eBay or something like that? Thank you.
Yeah. So we obviously, so the PhD student publishing the work, publishing the area, of course, of the actual material for the adhesion. That's a separate thing about the nano etching on that. In terms of the robotics, publishing on the kinematics of it and how it can be controlled and how it can be built. So it's publishing in all the areas on that. So the PhD, it's actually a few years ago, so the PhD's graduated now about 3 years ago. I think he's working somewhere in Europe on that, so he's already graduated. But yeah, so he published in that area. In terms of the robot kits, there are lots of them out there. My experience of them, or my opinion of them, they're generally very expensive. So, I mean, you can't blame the companies. The companies are setting out, they want to be a company to sell kits to people. I think my advice would be to try and maybe look at what they're doing, but choose parts separately and just make them yourself. I think there's no need to go and buy a quite expensive thing, which could be in UK pounds, maybe £1,000. The components probably are only £50, something like that. So it's a massive markup on these kits. So by all means, look at the kits, see what you get from them, but be quite sort of careful, because I think there can be a lot of money spent on kits that aren't required.
Good afternoon, Dr. Richardson. Once again, it was very vivid, informative, and educative presentation for all of us. And the swarm robots already, another audience has asked. And I would like to know if there is any nanorobots research is going on with your National Facility 1. And I have a couple of questions, and I will answer partly to his questions, if I may.
Yeah.
Okay. And is there any near-infrared vision system work or any vision system work that's going on with your research, innovative robotic systems? Thirdly, on robotic grippers for soft and fragile, the type and all the technology, any work is going on? Because I have worked in this, but I want to pursue my research work in that. So that's my area of interest. And the actual question was, what are the challenges that you face in a deep sea exploration of such robots when you're going there? I do understand long ago when in the Atlantic Sea, the flight data recorder, when they're trying to, it was very challenging at those times, at 80s, Atlantic Ocean, when Canadian, Indian Airlines went down. So what are you able to overcome the challenges with the current underwater or deep sea exploration robots with the present technology, or still the challenges are ahead and we are working on that? And to answer, Professor, I didn't get your name. Niranjan. I have been working on such, it's my hobby on the robotic side. There are plenty of such kits are available in the website in India. And competitions like, I don't know, since I was involved with first robotics competitions at US, you could encourage your engineering students and other students to take part in such competitive competitions which are done here also in Lego and FIRST. So they provide kits also on the time bound and the weekend mentors. You can find some people also who are interested could mentor on that. So FIRST stands for Inspiration and Recognition of Science and Technology, started by Dean Kamen. You may be knowing that the inventor of Segway and other technologies. Anyway, I was fortunate to associate with him to be in that technology. And if you could, on that research on this, I would be interested to continue my research on that. If I would be happy to communicate with you on this. Thank you. on near-infrared vision system or any vision system, as well as on robotic gripper technology for soft and fragile material. Thank you very much.
Okay, great. So let me answer perhaps in a reverse order. I'm not sure. So the challenges for deep subsea, so it's not the area we work on a lot, but as I understand it, really is actually to do with the localization. So robots, submarines are great. I'm talking particularly, I think, in terms of inspecting pipes, oil wells, that kind of thing. The robot technology to, once you're close to it, to inspect it, to even repair it is quite good. As I understand it, the challenge really is the underwater navigation, being able to get to places and be able to know where you are. So I guess a little bit like that I showed you with the water glider, although this is obviously more specific, you need to get to a certain location, is how can you really know where you are and where you're going. If you're fully autonomous, of course, right now, the remote control is not so bad or that kind of thing, but if you want to have a vessel, for example, an oil well or something that's fully autonomous, and maybe there are oil pipelines going out for 100 kilometers or so, how can you know where you are and track them? Of course, you can get close to them and you can try and visually track them, but as I understand, that's the biggest challenge for the subsea things. For the nanotechnology question, so the kind of scale we work at really is the scale that we say the scale you can touch and pick up and see. So not nano, small, and we can go down to millimeters sort of scale, not for full robots, for parts of robots, but we're not working in the nanoscale, so if you can't see it, you can't pick it up, we probably don't work on it. But it's obviously quite a large scale of things we do work on. For the soft robotic things, we work a lot in this area. Most of our work's actually in the medical domain, so I haven't really mentioned it that much, but lots of work to do with grippers, soft grippers, different ways of fabricating soft robots, but they're mostly for the medical domain. In particular, we're interested, of course, in terms of grasping material and tissue without causing damage. We have a lot of work in looking at conventional grippers and how they damage tissue and how soft grippers could be better in that area. And there was a last point that I can't remember. What was the last point? Oh, the vision. Okay, yeah. So we have a big group in vision. Lots of projects, AI for things like looking at pipes underground. So we have a big project. We're working on a big project that looks at it's called mapping the underworld. So there's a big challenge about knowing where pipes actually are from above the surface. So they're using sensors like ground penetrating radar and then trying to use AI to reposition them, which is kind of a vision system. We also have vision systems looking at navigation in cities, that kind of thing. So quite a broad spectrum of vision work. It's not my personal area, but it's working on the projects that I work on. Sorry?
Any underwater robotic welding you have pursuing or you are doing it? Underwater welding? Robotic underwater welding?
Yeah. So yeah, personally we don't do that kind of thing now, so we don't do welding. So we don't do a lot of industrial work, I guess I class it industrial. So we're interested in the technology, but not so much that kind of thing.
Good evening, sir. So I have a question regarding the research actually. You showed an example of an octopus. Yep. So where you apply a particular voltage for the movement where the cations just get attracted to one side of the plate and it gives the bending movement. So is there some scientific approach or it's ad hoc method in identifying the material? Just need some highlights on that.
Yeah, so this was developed around about I guess it was 20 years ago. So it used to be used in fuel cells. It used to be used in separating, I don't understand this particularly, but separating certain materials and that. So they found it about 20 years ago, and it was taken forward by a guy called Shahimpur. So I guess there's been 20 years of research refining it. So I was working in this area about 10 years ago, and it was nobody could make it, so I was one of the first, certainly in the UK, to actually manufacture the material. So taking the plastic, the challenge really is not so much the actual plastic or the polymer material, it's how you put the plating on. So you have to have a material that has obviously positive and negative that has to bend, and it's really hard plating process. So if you do it chemically, you have to use things like cyanide to plate them on that. So it's quite well developed now. You can make them from powders, you can make them from strips, you can buy them. It uses a thing called Nafion, which is that's a commercial name, but you can buy it. And also you can buy the whole thing with actually the plating on as well. So you can buy the plated things and you can buy the raw material. But the raw material, like I say, if you want to plate it, it uses things like cyanide, which is quite dangerous, obviously.
Our heartfelt thanks to Robert Richardson on behalf of Sahyadri family, on your gracious presence and encouraging us on your talk on the robotics. Thank you very much, sir. And also, I thank all the other dignitaries came over here from other colleges who attended his session. Thank you very much, everyone.